All right, so welcome to our third lesson of Calculus 2. So last time we finished learning about integration by parts, and we saw all these different situations in which we could use integration by parts, some of which are kind of surprising, some of which kind of defied its original intention as a sort of a product rule for integrals. Now today we're going to move on from that. We're going to do something quite a bit different. Today we're going to be looking at trig integrals, or trigonometric integrations. So that's lesson 3. So lesson 3, we're going to do integrals of trigonometric functions, and this, just like integration by parts, this is going to be a two-part lesson here. So let's remind ourselves of sort of the basic trig integrals. So hopefully you guys have seen these in Calculus 1 here. So the antiderivative of sine of x will be negative cosine of x plus c. And then we have the antiderivative of cosine of x. That will be positive sine of x plus c. All right, let's take a look at the antiderivative of tangent. Does anyone remember what this one is? What's the antiderivative of tangent going to be? Yeah, there's a few different ways of saying this. So it's natural log of absolute value of secant of x, or you could also say it's negative natural log of absolute value of cosine. And remember, both of these are the same thing right here. All right, and then if we look at the antiderivative of cotangent here, that's going to be natural log of absolute value of sine of x plus c. All right, and then we have the antiderivative of secant of x. This one was a little bit weird. Does anyone remember what this one is? Did you guys go over this in Calc 1? That's right. Natural log of absolute value of secant of x plus tangent of x, and then plus c. All right, so that's secant. And then cosecant's similar. It's going to be negative natural log of absolute value of cosecant of x plus cotangent of x. All right. So anyways, these are sort of the 6 basic trig integrals that we had from before. But the thing is that sometimes we want to integrate more complicated trig functions. So for example, maybe I want to integrate, I don't know, say sine cubed of x dx. Like how would I do that? And as we saw 2 classes ago, you can't just split up integration over multiplication. So I can't just split this into 3 sines multiplied together and then do it that way. And since I have a sine raised to a power, I can't just do the power rule here. So this isn't just going to be sine to the 4th over 4. That only works with x. So what are we supposed to do in this situation? Well, there are a few different techniques we can end up using for this. So today what we're going to do, the types of integrals we're going to look at today will be ones that look like this. The integral of sine of x to a power, and I'm going to call that power n right here. And then I'm going to multiply by cosine of x, and that's going to be raised to a different power, which I'm going to call m. And depending on whether n or m are odd and or even, we're going to have different ways of integrating. So there's going to end up being 2 different cases here. Okay, so case 1 is where one or both of n and m are odd. So if we have at least one odd number between them, then we could do what I'm about to do here. All right, so I'm just going to show you, this is best illustrated by example. So I'm going to show you this example right here. All right, so the first example I want to do today is the antiderivative or integral of sine cubed of x times cosine squared of x. All right, and this meets the criterion of case 1 here because we have 3, which is an odd power. Okay, so what are we supposed to do when we have something like this? Well, the first step that we're going to do is we break off one piece of the one that has an odd power. So what do I mean by that? Well, I'm going to break off a sine from here and move it to the end. So I have sine squared, cosine squared, and then I'm just going to put that sine I have at the end here. So I'm going to break off one from there and move it to the end. And when I do that, I should have at least one even power inside here. What I'm going to do next is whatever thing I pulled out here to the side, I'm going to change all of the other trig functions to be the opposite one. So I want to change everything to cosines. Now, what do I mean by opposite? I want to take a break and kind of explain what I mean by this. Some of the most common trig identities we're going to be using are called the Pythagorean identities. Does anyone know what the Pythagorean identity is for sine and cosine? That's right. Yeah, so we have sine squared plus cosine squared is 1. So this is the Pythagorean identity. All right. So that's the Pythagorean identity for sine and cosine. So that means that, say, I wanted to turn the sine squared into a cosine squared, what I'm going to do is I'm going to subtract. Where's my mouse? There we go. Be sure to have yourselves muted. Anyway, so what I can do here, the way I can turn the sine squared into cosine squared is I could subtract cosine squared over here, and I have sine squared is equal to 1 minus cosine squared. That's exactly what I'm going to do right here. All right, and then there are also two other Pythagorean identities as well, and we're not going to use them too much today because today we're just going to focus on sines and cosines. We'll do the rest of the trig functions tomorrow, or not tomorrow, Friday. But here they are anyways, so you can kind of think about them at least. If we take this equation and we divide everything by cosine squared, so if I divide all of this by cosine squared, then I have sine squared over cosine squared is tangent squared. I have cosine squared over cosine squared is 1. And then I have 1 over cosine squared. What's that going to be equal to? Secant squared, that's right. So this is another Pythagorean identity that we're going to be using quite a bit. Tangent squared plus 1 is equal to secant squared. So we can get this by dividing the original one by cosine squared. And if we divide the original one by sine squared, we have 1 plus cotangent squared is equal to cosecant squared. So this is also a Pythagorean identity as well. So when I say transform a trig function into its opposite one or the one in its pair, I mean switch sine into cosine or vice versa. I mean switch secant into tangent or vice versa. And I switch cosecant and cotangent. So these are called Pythagorean pairs, where we have sine and cosine, secant and tangent, and cosecant and cotangent. If you ever have these in the same integral, you're in luck because they're very flexible. They work well with each other. You could transform some of them into the other here. So that whenever you have these guys paired together, they're going to be nice. But if you have, say, like maybe a sine times a cotangent, that might not be as nice because we can't use the Pythagorean identity. All right, anyway, so this was all kind of an aside right here. So back to the integral here. So remember, we have sine squared times cosine squared times sine. What I'm going to do now is I'm going to change the sine squared, or whatever I just pulled my extra function here from, I'm going to change that into its matching pair. So I'm going to change the sine squared into 1 minus cosine squared. Okay. And I'm going to do that for every sign that I see in here. If I pulled a sine over here, I'm going to change all of the signs over. If I pulled a cosine over here, then I'm going to change everything away from cosines. So now that the only sign I see is right here, what I'm going to do next is I'm going to do a u substitution. So can anyone guess what my u is going to be here? What's u going to be? Yeah, it's going to be cosine of x. And we could see that because we have a lot of cosines in here. So that's our first criterion for picking a u. And the second criterion for picking a u is that the derivative of cosine is in here. That's why we saved this extra sign, because du will be negative sine of x dx. So we needed to think ahead and plan for when we were going to do this substitution. By the way, we don't have a negative in here, so I'm going to switch the sign here to be negative du is sine of x. Okay, so with this in mind, I'm going to turn everything I have into u's. So I have this extra negative that I picked up. I have 1 minus u squared, and then I have u squared, and then sine of x dx is now just going to be a du right here. All right, and this is actually pretty nice because I turned my trig integral into a polynomial integral. And that's going to be one of the big themes of this class. Polynomials are nice. They're the easiest things to do calculus with. So if you turn your integral into a polynomial integral, you're on the right track. So what I'm going to do now is, I'm going to get another piece of paper, and then I'm going to distribute my u squared and my negative. So if I distribute the negative, I flip the order of these two. So I have u squared minus 1 and then u squared here. And then I multiply by u squared. And then finally, all I need to do here is just do the power rule on each one. So I do the integral of u to the 4th. That gives me u to the 5th over 5. And then I do the integral of u squared. That's going to get me u cubed over 3. And then we're going to have plus c right here. And then finally, as with all substitutions here, we need to flip back to what we originally had. So I'm going to flip back to cosine here. So this is going to be cosine to the 5th of x over 5 minus cosine cubed of x over 3. And there we go. So that's how we're able to integrate a product of sines and cosines as long as one of them has an odd power to begin with. We do need that to be true. As long as one of them has an odd power, we're going to be able to do this. All right, let's look at one more example, and then I'll have you guys try one. So let's see here. Oops. Okay, let's do a slightly different example. In this case, let's say that both of them are odd. So let's say we have sine cubed of x and then cosine cubed of x. Now for this one, if they end up both being an odd power, then you're free to choose either one to contribute one of its sines or cosines to the end. So I guess I moved a sine there last time, so maybe I'll do a cosine this time, but you could choose either one since they're both odd. So we have sine cubed, and I'm going to pull off a cosine this time. Okay, so we did that. And then what do I do next? Let me ask you guys, what am I going to do now that I pulled off one of the cosines? That's right. We're going to turn this cosine squared into a sine squared using the Pythagorean identity. So whenever I have a cosine squared, I can change that into 1 minus sine squared. Okay. And then with that finished, I have a bunch of sines and one cosine. That means we're ripe for doing a u substitution. So I'm going to have u be sine of x, the thing I just turned into, and then du will be cosine of x dx. And thankfully, there's no pesky negative to deal with this time. All right, so turning everything into u's, I'm going to have u cubed times 1 minus u squared, and then cosine of x dx, that will all turn into a du. And then once again, I have myself a nice polynomial integral. So if I distribute, I have u cubed minus u to the 5th du, and I could do the power rule here. So I have u to the 4th over 4, I raise the power, divide by the new power, minus u to the 6th. I could raise this to be 6, divide by the new power. I have plus c. And then finally, I finish things off by plugging in my sine back in for u. And there we go. By the way, if we would have done this problem slightly differently, if we would have done it where we moved a sine to the end, you would actually get a different looking answer. So your answer would have a bunch of cosines in it. But technically, they would actually be the same function. You could use the Pythagorean identity to convert that answer into this one. and vice versa. So if you get a different answer from your friend, you did it a different way, doesn't mean that one of you is wrong. It just may be a different version of the same answer.
Professor Manley, quick question.
Hmm?
On our test, because it's multiple choice, if we choose the wrong one, does that make a difference, like within our answer?
If there's some kind of like ambiguity like that, we'll steer you towards one choice or the other. Yeah, so don't worry about doing it correctly and then ending up with the one that doesn't show up. Yeah, don't worry about that.
Okay, cool. Thank you.
All right. So why don't you guys try to do this now? So why don't we open up Canvas or take out a piece of paper and enter it into Canvas later. Our first practice problem will be doing the integral of sine to the fifth of x. And there's no cosines in this one, it's just sine to the fifth of x. Now, it turns out that it doesn't really matter that there aren't any cosines. We can just imagine that the power of cosine is 0 for this one. So we can kind of do this in exactly the same way that we did the other two. So go ahead and give this a try. And yeah, you can type your answer into the chat if you want. Remember, don't forget to put this in on Canvas, but don't submit it yet because we're going to have another question later. Does it matter what trig identity we use? Yeah, I'm pretty sure the Pythagorean one's the way to go here. Probably that one. All right, we'll see if that's the correct answer in a second. Why isn't it just sine to the sixth over 6? The power rule only works if it's x raised to a power. If it's anything else raised to a power, the power rule doesn't work. To kind of see why that is, take the derivative of sine to the sixth over 6, and you'll see you won't get back to sine to the fifth. Yeah, it worked for u because u is the variable that we're integrating with respect to. So if you ever have something that just matches whatever this is, then you can go ahead and just do the power rule. I'll give you guys another minute or so. Who came up with this method? I am not sure at all. All right, why don't we see how to do this one? So it is a little bit different since we don't have any cosines in here. All right, so we see that we do have an odd power of sine, so we could still use this method. So what we're going to do is we're going to break off one of these sines right here. So I have sine to the fourth left over, and I have sine of x here. All right, once I have this piece broken off, I'm going to change all of the other functions to be the opposite of this. I'm going to change everything else to be cosine here. Now I have sine to the fourth that's not quite ready to use the Pythagorean identity on. I need to exploit the basic fact that sine to the fourth is sine squared squared. So once I recognize that, then I can change this sine squared to be 1 minus cosine squared. All right, wonderful. And then now that everything else is either a constant or a cosine, I can go ahead and do my substitution. So u will be cosine of x, and du will be negative sine of x dx. But once again, I don't see really a negative here, so I'm just going to move the negative over to the du. All right, so when I do this substitution, I have this extra negative I got, and then I have 1 minus u squared, and that itself will be squared. And then sine of x dx, oh, thank you. Sine of x dx will be du. All right, so I'm going to FOIL this part out. So I have 1 minus 2u squared plus u to the fourth. And then I'm going to apply the negative. So I'm going to have minus 1 plus 2u squared minus u to the fourth right here. All right, and then now I just have a basic polynomial. Now I can just use the power rule. All right, so I integrate negative 1 and get negative u. I integrate 2u squared to get 2/3 u cubed. And then I integrate this and I have negative u to the fifth over 5. And then we have plus c. And then finally, the last thing we do is we just switch everything to be cosine, since that's what we selected for u. So I have negative cosine of x plus 2/3 cosine cubed of x minus cosine to the fifth of x over 5 plus c. All right, so I think I saw that in the chat. I think that was what H said. So yeah, that's how we do this one. And be sure to write this down so you can punch it into Canvas later or now. All right, great. So that's the case one here. So that case applies when one of the powers is odd. So what's the other situation? Well, the other situation opposed to that is when both of them are even. We don't have an odd power in sight. So case 2 is where both powers are even. And unfortunately, this case is a little bit more difficult to deal with than the previous one. So let's take a look at an example of this. Let's see, where did I put that? Oh, here it is. Okay, so let's say I'm going to do the integral of sine squared times cosine squared. All right, so this is the integral I'm going to do here. Now the thing is if I try to do the technique that we just did, if I say break off a sine or something, then the leftover power of sine here will be odd, and that means I can't use the Pythagorean identity because that has squareds in it. So that's the reason why I can't use the previous technique on this integral. So what are we supposed to do here? Well, in this problem, we're going to use a different trig identity to help us. And these trig identities, there's actually 2 of them. These are called the half angle identities. All right, so what are these guys? Well, if you ever have a sine squared of x and you really just want to get rid of that square, you could do so. You can change it into 1/2 times 1 minus cosine of 2x instead. And notice that there's no square on this side. And cosine squared has almost exactly the same formula, only it's just going to be a plus in there instead. And one thing that kind of confused me at first when I learned this is that it's still a cosine for the sine one. It's not 1 minus sine of 2x, it's cosine for both of them. The only difference between them is that sine has a negative, cosine has a positive. So what we're going to do is we're going to change all of our even powers of sine and cosine into these guys right here. And we'll see how that helps. So sine squared is this, 1/2, 1 minus cosine of 2x. And then cosine squared is 1/2, 1 plus cosine of 2x. All right, so let's simplify this a little bit. Let's see if this made the integral any better. Let's see, I have 1/2 times 1/2. That's 1/4, but that's just a constant multiplied by this. So I can move that out to the front. So I have 1/4. And then if I FOIL these two together, let's see, I have 1 times 1 is 1. 1 times cosine of 2x is cosine of 2x. And then I have negative cosine of 2x times 1. And that's pretty nice because then those will cancel out. And then finally, I'm going to have negative cosine squared of 2x because I multiply these together right here. Okay, now it looks like we're almost good to go here. We could definitely integrate 1. That's not going to be a challenge. But the problem is that we have another cosine squared here. So we didn't get rid of all of the squares. We ended up getting another one from what we just did. So what do you guys think I should do now? What do you suggest that I should do to fix this? Do it again. That's right. Yeah, we're going to end up doing this again. Whenever you have a square that you don't want with a sine or cosine, just use the half angle identity. And we can even use it again here. Okay, so we're going to have 1/4, and then we have 1, and we're going to have minus because of that minus. Now, cosine squared of 2x puts a 2 inside here. And whatever goes into this x goes into that one as well. That means I'm going to have cosine of 4x once I put this in. So I'm going to have 1/2, 1 plus cosine of 4x. And that's because of this 2 that we already have. We end up doubling whatever angle we have there. Okay, so let's clean this up with a little bit of algebra here, and then we should have an integral that we can do. All right, so let's see here. So if I do negative 1/2 times this, I get negative 1/2. If I do negative 1/2 times this, I have cosine to the 4x over 2. Now, if I do 1 minus this 1/2 right here, then I'm going to end up with 1/2. So I have 1/4, and then I have 1/2 right there because I do this and this combined, and then I subtract cosine of 4x over 2. Okay. And then now this is an integral that we can actually do here. This is a Calc 1 integral. All right, so let's go ahead and do this. So I have my constant, that's just going to stay there. The antiderivative of the constant is a constant times the variable. And then the antiderivative of cosine is going to be sine. But whenever we have a coefficient inside here next to our x, we also have to divide by that. So I'm going to divide by 4, and combined with the 2 I already have means I'm going to be dividing by 8 total. So then I have plus c right there. And then I guess we could leave our answer like this. We could even factor out a 1/2 if we wanted. So we have 1/8 x minus sine of 4x over 4. Maybe that's more appealing to some people. But either way, we managed to integrate this guy. So the moral of the story is if we have case 2, where everything in sight has an even power, we repeatedly apply these half angle identities here until we don't have anything that's squared anymore. And then we could just do a normal Calc 1 integral. All right, let me do one more example of this, and then I'll have you guys do one. All right. Yeah, so pray that we get case 1. Yeah, I'll fully admit that case 1 is definitely easier and less time consuming than this one is. All right, so example 4. So this one, I'm just going to do the integral of cosine to the 4th of x. There's no sign here. All right. Well, whenever I have a 4th power or some higher even power, I'm going to rewrite this in terms of cosine squared so I can use the identities. So I have cosine squared of x, and then that itself is squared. Okay, Now this time, remember, I'm not using the Pythagorean identity here. I'm using the half angle identity right here. So cosine squared is going to turn into this right here. So I have 1/2 times 1 plus cosine of 2x. And all that's going to be squared. How did we get, I think someone asked about how we get the 1/8 here. So remember, when you integrate sine or cosine of a number times x, you have to divide by this number right here. So we divided this by 4, and we already had a 2 down there, so that's going to be an 8. All right, anyways, so now for this problem, I have this guy right here. This is cosine squared from the half angle, and I need to square that. All right, well, I have this constant 1/2, which I'm squaring, which will turn into a 4th. And just like the other problem, I'm going to move that out. Then I'm going to FOIL 1 plus cosine of 2x with itself. And when I do that, I end up getting 1 plus cosine, or 2 cosine of 2x plus cosine squared of 2x. So that's what happens when I FOIL this right here. Okay, so let's check this. We did our identity, we simplified. Now let's see if this is actually something that we're going to be able to do here. Well, we could definitely do the integral of 1. That's not going to be an issue. We could do this integral the same way we did that one. We just change this to a sign and then we divide by 2. The only one we can't really do right now, or at least we couldn't do in Calc 1, is this one, cosine squared of 2x. So just like in the previous problem, if we have any remaining squares of trig functions or even powers of them, what we're going to do is we're just going to use the half angle formula again. So let's do that. We have 1 plus 2 cosine of 2x plus, and then here's my second application of the half angle. So cosine squared will be 1 plus cosine of twice whatever is in here. So we already have a 2x, so now this will be a 4x. Okay, so now we have that. Let's clean things up a little bit before we integrate. So I have 1 here, and then I have 1/2 times 1 here. So this is going to be a half. This is going to be 1. That means my constant term in here is going to be 3/2. And then I have 2 cosine of 2x still. And then finally, I have 1/2 times cosine of 4x. All righty, so now this is about as nice as we can get it. So now we're going to integrate. All right, let's see what we get. So we have our constant. We integrate this constant to get 3/2 x. And then we integrate this right here. We raise this to be sine, but then divide by 2. That cancels the 2 right here. So we end up with just sine of 2x right here. And then I integrate cosine of 4x. Well, the integral of cosine is sine. But because of the 4 right there, I need to divide by that. So I divide by 4, and I already had a 2 down there. So this is going to be an 8. And I have plus c. And unlike the other time, it doesn't really look like I could factor anything nice out of this. So we'll just leave the answer like this here. All right, how did I get the 3/2? Yeah, so again, my algebra here was I did 1/2 times 1. I distributed here, and I got positive 1/2, and then I added it back over to this one right here. All right, there we go. So we managed to get our derivative of cosine to the 4th of x. All right. Why do you get a cosine of 4x when you're doing the second half angle? Well, the half angle identity is cosine squared of something is 1/2 times 1 plus cosine of 2 times whatever was in here. So if I already had a 2x in here, then it's going to be 2 times 2x right there. And that's going to give us 4x for this. So that's why we have 4x in these situations here. All right, wonderful. So that's the second case. And unfortunately, the second case is a bit annoying because you have to repeatedly use this half angle identity. And the higher the powers get, the more that we have to FOIL and use the identity here. All right, so I'll give you an example of this to do. And This one will actually be a little bit easier than the two I've just done. So let's do our second practice problem. I just want you to integrate sine squared of x. So why don't you guys go ahead and give that a try. All right, seem to have some agreement in the chat. See if you guys are right. All right, let's take a look at this guy. I don't think this one will take too long. So sine squared, well, we have an even power of sine, and technically we don't have a cosine, so that's cosine to the 0, which is also an even number. So this is going to fall into case 2 here. So we change all of the instances of sine and cosine squared into their half angle versions. So the half angle version for sine is 1/2 times 1 minus cosine 2x. So it's almost exactly the same as the cosine one, only there is a minus there instead. All right, I'm going to pull the 1/2 out. And fortunately, this time we don't need to repeatedly use the half angle identity. So that's kind of nice. We don't need to do any additional manipulation here. So I'm just going to integrate this. The integral of 1 will be x. The integral of negative cosine of 2x will be negative sine of 2x divided by 2. And there we go. There is our integral of sine squared right here. All right, that's the end of the notes. I'm actually going to do one more example here so we get a little more practice with this. And this example is going to actually combine integration by parts with what we just learned. And that's something we'll be seeing more and more, is that the more techniques we learn, there will often be problems where we have to use multiple techniques in order for this to work. So I'm going to do one of these extra problems I have. And what I'm going to do is the integral of x times cosine squared of x here. Now, what I'm going to do here is, since we just learned how to integrate even powers of sine and cosine, I'm going to end up making this be my dv, and then this is going to be my u. And the reason why I pick that is I tend to like to pick polynomials to be my u, because those end up, those end up differentiating to 0. So they get simpler as you go along. All right, so if u is x, dv is cosine squared of x dx, well, then that means that du will be dx right here. And then v, well, that means we need to integrate cosine squared. So kind of off to the side, kind of similar to the problem that we just did, we need to integrate cosine squared. Actually, I'll just do it over here. So the integral of cosine squared, we're going to use the half angle identity. So it's 1/2 times 1 plus cosine of 2x. Okay. And then this is almost literally exactly the same as this, except this has a plus and that has a minus. So that means that the answer will be exactly the same, only instead of this being a minus, we're going to end up getting a plus. instead. And this is exactly what we're going to put right here. X plus sine of 2x over 2. And that's going to be our v for this one. All right, how did you immediately know we needed to use integration by parts? One guess is that I have a product of two different functions here. That's a good time to think about integration by parts, especially if they're different from each other. Like maybe if this was a sine times a cosine squared, I can maybe do a u sub in order to do that. But if they're totally different and they're multiplied together, then integration by parts might be a good strategy. All right, so now I'm going to use the IBP formula. So our original integral is going to be u times v. So it's going to be 1/2 x times x plus sine 2x over 2. And then I subtract and I do the integral of v du. That's going to be this integral right here. So this minus came from the fact that I'm using integration by parts right here. And then this 1/2 kind of came outside of the integral. All right, so I do need to integrate this stuff, but thankfully this is going to be a not too bad of an integral to do. 1/2 x times x plus sine of 2x over 2. All right, so we integrate x and get x squared over 2. Like that. And then I have the integral of sine of 2x will be negative cosine of 2x. And then I divide by this 2. But since I already had a 2 down there, that's going to be a 4. And there we go. So there's our answer for this guy right here. So sometimes we may end up needing to combine several of our techniques together. And that'll be more and more true of the techniques we're going to learn later, because those are kind of based foundationally on the ones that we're learning now. Let's see. So we have a question. Is IBP sort of the product rule of integration? That's an excellent way of thinking about it. And if you remember, integration by parts actually came from the product rule for derivatives. So it is closely related to that for sure. All right. So I did everything that was on the worksheet and I did an extra one. Let's see here. Oh my God. Last semester, people asked a lot more questions. So I think this ended up going a lot more here. Yeah, does anyone have any questions on what we've done? Anyone want me to go over any steps that were unclear from before? Everyone's okay? Everyone in the chat okay? All right, well, let's keep the streak going. Yeah, so everything's finished now. So I will see you guys on Friday when we will learn about how to integrate the